Hello, welcome. Today we will be going through the advanced RAG overview, and we'll be talking about unfreezing a frozen RAG pipeline. So some of you might be wondering what that means, and we'll get into it. I guess just in terms of some housekeeping, there is a forward-looking statement here. And then just as a way of introduction, my name is James Lin. I'm the head of AI ML innovation for Experian. And speaking with me will be Jason Lee, one of my generative AI engineers. If you're not familiar with Experian, what we do is we do credit scores, obviously. But our kind of motto is financial power to all. So we want to empower customers to take control of their financial future. And in terms of generative AI, we have 4 models in production in North America today. So what we're hoping is that we'll be able to share some of those kind of learnings with you. But we won't be talking about anything Experian specific. We'll just be talking about kind of the technology here. So to kind of open up, we were fortunate enough to get one of the early slots. So I'll lead off with a quote. This is from one of my friends, Andre Vargas, who is the CDO of Creative Artist Agency. And he's kind of very inspirational. He likes to say funny, quirky things. So this is kind of one of those things that he said. So you might have heard about FOMO. Obviously, you guys all know that. It's fear of missing out. But with generative AI, we have JOMO. So JOMO in this case means the joy of missing out. And what we're looking for here is essentially, we're hoping that you take some of the things that we learned in the pain points, and you're able to take it back and apply it to something that you can do yourself. And our goal with this presentation is that you have something that you can really apply when you walk out the door. And feel free to talk to us afterwards. We're really open to collaboration on these things. So just to kind of set the stage before we get into everything, this is just kind of the review in case you're not familiar, but you're probably all familiar with this slide for RAG. All the earliest Hugging Face examples have some form of it. So in this case, you have some documentation that you're creating embeddings out of. You stick those into a vector DB, and then those embeddings are used by the generative AI model to give context to the model to answer. But for our presentation, we have to go maybe one level deeper. So in this case, we'll break everything out. So the first step is embedding. So as we said before, we have the documents. And with the documents, you have to break them up into chunks, usually 512 bytes. And with that, there's an embedding model, which is what's used to create the index, which is stuck into a vector database. I'm going to go through this kind of fast, by the way. So, and then on the inference side, when you get the prompt from the user, you then also use the same embedding model to index the prompt. And then that's what's used to do the lookup in the vector DB. And that is how it kind of actually performs. So if you look at the whole picture, we stick in the embedding. Essentially, it's one system or one pipeline, but just kind of like an expanded view of that. So I think the next thing is we opened up saying there's this concept of frozen RAG. And this was pioneered by, I'm probably going to butcher the name because I only read, I don't hear. But it's Thawing, who actually invented RAG. Like kind of the first phase RAG systems that we're all dealing with, he says, are frozen, which is why we're not able to kind of achieve high results. So what exactly then do we mean when it's frozen? So maybe the first instantiation of that is, well, once you deploy to production, you have essentially the vectors, the data that you're putting in there, everything there is stuck, right? Like when you're in production, you can no longer change whatever you have in your vector store for that use case. So it's basically whatever you have is only as good as what you have when you did that deployment, and you can't change this anymore. But maybe if you start going into it, you might think other things are frozen as well. So in this case, we can look at the embedding model itself. So like when we first started out, there was maybe only 1 or 2 embedding models. Now there's probably a dozen or more that people use. What are the differences between the embedding models? Like, can we change that? Or do you even want to, like, say, tune an embedding model? But also the LLM itself. I think in the beginning, we were all very focused on just using one LLM for each RAG system. But in more advanced use cases now, we can even switch the LLM. And then I'll challenge you even further. What if we can change what the user asks? Or what if we can change documentation? Like when we started out saying, hey, once these vectors are stuck in your database, you can't do anything. But is that really the case? Can we actually change the documentation? And can we change the prompts that the user are asking us? So basically, the whole system is frozen. And when you get a bad kind of RAG result, we kind of have this model of saying, hey, like, when you get this challenge, you're basically, how do I fix this? And usually, a lot of times, you're basically stuck saying, hey, there's a prompt, and I got the wrong answer. So why do I have the wrong answer? You have to break out kind of the whole RAG system into the steps. And within those steps, that's how you debug like if something is wrong. So the retrieval, meaning when you're using your embedding algorithm, are you finding the right or the best embedding to answer the question for that user? So again, this kind of goes back to the fact that maybe the embedding algorithm was frozen when you started out. Within the context, this is maybe like the data that we were talking about in the beginning. So the embeddings that you created in the vector DB, are they accurate? Are they complete for the question? And maybe most importantly and overlooked is, are they time relevant? Like, did kind of the answer change over time? Did your policy change? And maybe sometimes it's, hey, did the embedding to answer this question actually even exist in the system? Because we found that it wasn't all the time. And then finally, we go over generation. That's obviously the model. So when you are generating the model, did we have the correct answer? Was it the correct length for that use case for your product? And did we talk about it in the right tone or style that we were expecting? And maybe more so, I hate to use the word hallucination here, but it's a big topic, obviously. So are we willing to accept additional knowledge that the model is imparting based off its training data, in addition to maybe the embedding knowledge that we're trying to stay on our own? So I will switch to an enterprise context, because maybe this is where we're coming from as Experian. Maybe some of you are more advanced than we are, because we're not. We are kind of stuck to enterprise. So I hope this resonates with some of you at least. But we'll go back to kind of this first flow that we opened up with. So I think if we backtrack maybe 2 years ago, when we were first looking at RAG architectures, we probably were in this world where OpenAI is saying, hey, ChatGPT or GPT 3.0 at the time is the most advanced model in the world, and everyone is going to build out their own like enterprise GPT, which would be like one single model to rule them all type of thing, right? So if we enter RAG in this case, it's just this simple view. But maybe even 18 months ago, I think we started to talk about this thing called agents, or we at least moved away from the idea that there's only one LLM or model that is going to be accessing your RAG or vector database. I think for a long time, people are kind of stuck on this architecture in terms of like how we're deploying to production. And this is probably kind of a key issue for enterprise systems. But what I would call this is a monolithic vector database. And there are some pros to this from a enterprise perspective. So yeah, I mean, the maintenance of it is very easy. Like everyone just kind of embeds their own vectors into it, and we're good. We don't really have to manage too much. And maybe more importantly, the access. Like if we have one single vector DB, then you can reuse the things that other people had put in already and prepared for you. And maybe you didn't have access to that data yourself. But there are cons to this also. So what you find is if you have a single vector DB, you start getting repeats of the same embeddings. Like what are kind of the embeddings that we're creating? They're like PDFs or Word docs, or I guess a popular example is Finance Bench, where they're like 10K of different companies, right? So from year to year, how similar are these 10K documents to each other? Like, there's probably 80% overlap. So how do you know that like the one that you have, the embedding that you got is the right one for that year? And you're basically making that retrieval problem that we had like spun out on its own a much harder problem to solve. So this kind of time-sensitive aspect is what makes it really challenging in this perspective. So we propose maybe a more advanced enterprise architecture, RAG. So what does this mean? So I mean, we could still have maybe some sort of monolithic perspective here, but instead of maybe being a vector DB, what if instead it was just a storage mechanism? In this case, it could be your data lake or Delta Lake, right? Or Lakehouse, however you want to call it. But from there, when you deploy, each GenA app that you're making, you might want to kind of curate and do some data operations to do a bespoke vector DB for that particular application. In this case, when you're kind of deploying, this is probably more extensible. So we'll proceed with this model for the examples that we give to you. And before we kind of get into everything, and I'm wrapping up, so we will get to the more interesting bits soon. Some of the critics for what we're saying might ask, oh, but isn't RAG dead, right? And I think based on how many of you are here, I would say maybe not, because you're all very interested in this topic. But for enterprises, it won't be the case, and I'll explain why. So what are the things that kind of the critics might say, right? So the first is RAG is unnecessary or eventually will become obsolete, right? Like our foundational models are constantly improving, and at some point it'll know everything. But if you say that for enterprise, I think that's really scary, right? So we'll talk about this later. The second thing that someone might say is, okay, well, with these agentic systems now, like why do we need RAG? We can just build an agent that's going to query the exact structured data that we need, and based off of that structured data, we'll be able to answer the question. And yeah, that's true, but that doesn't mean that you don't need RAG. That's pretty much all I'll say there. And then the final thing, and this is still RAG, but kind of one of the things that people say about RAG is, hey, graph RAG performs better than regular RAG. So, well, first of all, it's still RAG, but second of all, I think if you see someone who has taken graph RAG to production, what they end up inevitably doing with the architecture that we had said previously is that the graph relationships usually are only 3 layers deep. So you can actually do your data operations for your use case specific vector database and embed the vectors into that use case specific thing. So you kind of get the benefits of both. And this is why enterprises will always use RAG, as we said. So essentially the first thing is, hey, there's this domain-specific data that we want or are very interested in. And kind of systemically, if we create the architecture that I had gone through, then it's actually easier to deploy and transfer expertise to like kind of this shift left concept, right? Like once you've set up that architecture, even though it might be a difficult problem, this is something that you can then transfer on very easily to like your teams. And finally, there's this kind of concept of the data moat, which goes back to the first thing, which is enterprises are very protective of their data and their expertise. So in that case, we want to protect kind of the castle or the core business logic. And the data, or the RAG database in this case, is kind of functions as this moat that will protect the enterprise, at least how we think of it today. So what we're looking at here and kind of summing up here before I hand it off is that we consider RAG to be the entire system, and more so that the data is foundational to that system. So we do take a very data-centric approach to this. And to kind of run through those examples, I'll now hand it off to Jason, the much more interesting part of this presentation.
So my name is Jason, and I'll be talking you guys through some of the pitfalls with a frozen RAG system and how we can break the system down into individual components and see if we can start addressing some of the problems. So a lot of the complaints against RAG is really just against frozen RAG. And we identified some issues with frozen RAG and kind of separated them into 2 categories. And the first one being out-of-the-box models. So with these out-of-the-box models, the first one is the large language model, right? That's the generative module of a RAG system. So in the case of RAG, hallucination takes on a different definition because anytime the model relies on its built-in knowledge, we refer that as hallucination. Because that's a big red flag in a RAG system because you don't really know where the generation or the answer is coming from, whether from like the context the model is given or its built-in knowledge, right? And that's kind of destroying the reliability of a RAG system. You're kind of just going back to the original foundation model only kind of Q&A system, right? So, and that faithfulness of the LLM, it can be addressed using supervised fine-tuning, and we'll talk about it in a little bit. But for the embedding models, it faces a different issue because you actually need the embedding models to know your data, unlike the LLM is more of a behavior fix, right, the faithfulness. So because the embedding models actually need to map a query to the relevant chunks. And the intricacies within your own data are not captured in the training of these general domain embedding models. So again, the fine-tuning is required even for these embedding models as well. And the last piece is these user queries are really messy in the real world. And they're not messy in the sense that they contain typos, but they're messy in the sense that they often contain multiple parts, even in a single sentence question. And even worse, sometimes the users themselves don't even know what they want out of your system. So you need to, that would take some sort of query decomposition or query rewriting. And moving on to the right-hand side of the slide, we believe data is really important. It's foundational to any well-oiled RAG system. That's why I put it in its own genre. And the first point is the source documentations, even nowadays, are still written with human readers in mind. And what that means is that tables and images are still prevalent in these documentations. And these even frontier LLMs are not as adept at reading these, at least not as well as they are at reading text data. And sometimes the information in these source documentations, they're written with the assumption that the employees within your organization or the coworkers know certain things about your company, right, or your enterprise. Right, so they're kind of just glared over in the source of the documentation, and which is not as apparent to out-of-the-box LLM. And the second point, which is the most common case in our experience, is that the true answer may not even exist in your documentation, right? So you kind of just need to add documents there on your own. Or because the second point gets tied into the third point is when the outdated information get passed into the LLM, which pollutes its context window, right? Because it's hard for a human to distinguish older data and newer data, let alone an LLM when that's all it sees, right? So that the order I just talked these issues in LLM, embedding, and data, that is intentional because this is also the order in which we did evaluation or in which we do evaluation. Because only when you can trust what the generative module is saying, right? It's staying faithful to the context. That's when you can really isolate the retriever module. And then once you fix the embedding model, then some of these data gaps will be surfaced later on. So that flow is very important to our evaluation as well. So the ideal state of a domain adaptive RAG, which is the opposite of a frozen RAG, is as follows. And I kind of just listed the properties or the solutions under model, data, and strategy. And for model and data, I'll kind of walk through some of them already. So for the model, I'm just going to quickly go through it. So I listed some of the papers in the brackets, square brackets, so you can, the actual papers are listed at the end, so you can kind of peruse them over at your own leisure. But for SFT, for the LM, what you need to instill is the behavior you want, right? The faithfulness or the tone, the length of the response. And for the embedding model, that's the part that you actually need to instill the new information into the embedding model, which requires some sort of contrastive learning. And I listed what we used in the slide there. And I'm gonna glance over data because I already talked through it in the last slide. So once you have well-tuned models and all the holes in your data are are plugged. Well, this is the strategy part is what we didn't really realize at the beginning when we started the project. So the strategy part is what we really realized that will get you through the finishing line in terms of customization to your own, to your needs or your application. So we look at it through 3 lenses. And the first one is when to retrieve. So when someone says retrieval or RAG, they automatically assume the retrieval is done at the very beginning, which is kind of an old view of RAG, because recent research has shown that when you do retrieval throughout the generation, it's actually better for the model, especially when it's presented to the model when it needs it. And I'll show an example of that later. Or you can think about what to retrieve. So from this case, I already talked about multi-query, which is basically query decomposition, right? So you simplify a complex query into simpler ones. Or you can think about using multiple vector indices, right? So if you have some sort of inherent structure within your data, you can kind of enforce that onto your vector index as well. So this is kind of similar to a GraphQL idea because the structure that's inherent in the multiple vector indices setup. Or the last piece is what to generate. So a lot of people think RAG just in terms of one shot, right? So the model sees the context once and then generates an answer, right? But you can also have some sort of a chain of thought, right? If you don't have any latency requirements, right? So you can have the model reason over the context and then generate a more detailed or better answer in general. And the last piece is kind of new, is few shot, and it's not the few shot prompting you often see in prompt engineering. Few shot in the case of RAG is more of a reflection type of generation. So you have the model. A good example of that is self-RAG, which you have the model like look over its past generation and then reflect on it and see if there's more required or how to fix its past generations and stuff like that. And I will show an example of this later. That's more of an implicit reflection in the examples later. And so this slide, I basically took one of James' slides, if you recall, in terms of retrieval, context, and generation. And I combined the solutions from the last slide, and I just put them under the problem each one actually solves. So in order to read it, so for example, retrieval, if you have retrieval problems, basically you can try re-ranking or fine-tuning the retriever, the embedding model, right? Or you can try some sort of query decomposition or rewriting just to lessen the load, the workload on the embedding model. And I'm not going to go through the rest because the solutions I already talked about, but this is just more of a practical view of the same information. From here, I'll be walking you guys through some of the examples that we came up with. So in this case, the problem setup is we have 15 research papers on the topic of Gen AI. We have 3 categories with 5 papers each. And this is our custom data set. And the query that we designed is meant to replicate some of the issues that I already kind of walked through. So namely, sometimes the users don't prompt the RAG system correctly, right? Because this is if you look into the question, this is a comparison question between Dragon, which is a RAG paper, and Orpo, which is the reinforcement learning paper. So this is a 2-part question in a single sentence, right? So RAG is notoriously bad at this type of question. And also another problem is that since all 15 papers are on the topic of Gen AI, within these papers, they contain paragraphs or sentences that carry the same semantic meaning, right? So they have overlapping information and therefore overlapping embeddings. So if you want to do precise retrieval, meaning you want to pull the exact paper that a question is asking for, you need to do some more magic under the hood in terms of RAG. So what we're going to do is we're going to start off with the most simple question, the most simple setup, the vanilla setup that James mentioned, and then also some housekeeping things. So for the generative module, we're using Quinn 4 billion, just so I could run it on my own computer. And all for the vector indices, they're all Databricks vector search. And the embedding model is the GTE foundational API on Databricks. And just to illustrate the problem further, so from the most vanilla model, you can see I included the context, the embedding model retrieved, and the model response at the end. And just so you can have a clearer picture of what I'm talking about. So, So immediately that jumped out at me is the model is retrieving correctly one of the papers, right? It's pulling the paper Dragon, right? But the glaring miss in the context is there's no ORPO, right? That's a problem because the model needs to see both papers in order to generate a good answer. And the question marked in red basically reflects that, right? Because the LLM in this case is surprisingly faithful because it's saying, I don't really know about ORPO because it's not being given to me. It didn't just say anything out of its own knowledge. So if you follow the flow that I mentioned at the beginning, LLM, embedding, and then data, LLM in this case is pretty faithful. So we can just focus on the retrieval piece. So I think the issue right now is that the retriever model is not only facing a complex question, but also has different overlapping embeddings, right? So let's see if we can sort of impose the structure we already know about the data, which if you recall is the 3 categories, right? We have 3 categories of, on GenAI, RAG, reinforcement learning, and vision, right? So if we can impose that structure onto the single vector index. So what we did was to basically impose the categorization onto the vector index. So right here, we have 3 vector indices. We broke the single vector index into 3. And along with it, we have the description with the vector index. So the LLM will know which one to pick given the description and the query. And so the model output from this setup, as you can see here, so each retriever is still doing the top 3 chunk retrieval. So that's why there's 6 chunks. And so if I can direct your attention to the top line here, so the model selected RL research paper and RAG research paper, right? So the correct 2 domains that the question is asking about. So from these 2 domains, 3 questions or 3 documents are retrieved for each one, right? Because you're kind of essentially forcing the retriever to select one from each category, right? So you're therefore solving the problem of just retrieving the Dragon paper. So now you can see the Dragon paper is still selected, but along with it, we also have a reinforcement learning paper. However, in this case, it's not retrieving the ORPO paper, right? This is retrieving an AI feedback paper. And, go back. So the model is still, in the response, is still summarizing what Dragon does, and it's also summarizing what the AI feedback does. But at the end, it's saying, I'm still not provided the paper ORPO. So like I mentioned, the next step, we framed the progression in terms of crawl, walk, and run. I forgot to mention that. But we're still in the crawl phase with the multi-vector index setup. So the next phase is to walk, so to speak, right? And how do we walk is by breaking down the complex question into a multiple or 2 simpler ones. And the way we did that is just to use pretty simple query decomposition. And we included few-shot prompting just to show the model of how we want to do this kind of decomposition. And the purpose of this, is to lessen the burden on both the vector index and the retriever. So after we did that, you can see the ORPO papers and the Dragon papers are both correctly retrieved, and therefore the model response is the best response so far. So now we're walking, so to speak. But we didn't just want to stop here. So figuring out which moving parts to pick takes a lot of data science hours. So we try to figure out a way to really reduce the load, make it more user-friendly. And also the purpose of this talk is also to unfreeze all the components of the RAG system. So we kind of really wanted to push the boundaries of what's possible. So what we did here next in terms of the run phase is we try to unfreeze all the components of a RAG system. And by all the components, I mean, if you look at the heading, it's when to retrieve, what to retrieve, and what to generate. So these are the 3 strategic perspectives that we talked about. And so the purpose is to give the model control to decide all 3 just by its own, right? So essentially you obviate all the data science hours that's required in picking them. So the way we did that is we implemented the paper Dragon, and it stands for Dynamic RAG based on the information needs of LLMs. And you can see the 3 main ideas from the paper listed in the bullet points. they will correspond really nicely to the three strategies. So let's go through when to retrieve. And the way the model decides when to retrieve is it only activates the retriever module when the LLM generates an uncertain yet significant token. So how do we determine these two criteria? So that's why I attached the pseudocode on the right of the slide. So the way we determine the significance of a token is that we need to look under the hood of the LLM, and more specifically, the attention matrix of the last transformer layer. So the way I think about attention matrix is really just a way to tell how much a token is paying attention to other tokens, or vice versa, right? So if you look into the code a little bit, it's trying to extract the maximum impact of a token it has on the future context, because it's looking down the column of the attention matrix. So that's how we determine the significance of a token. Again, it's by looking at how much impact it has on the future context, or the future tokens. And how do we determine uncertainty of a token? It's by looking at the entropy of the probability distribution. So if you recall, an LLM basically generates a probability distribution over its entire vocab, right? And it just selects one token. So when every time you encounter a probability distribution, you will encounter entropy, right? So for example, if you have a token that with a probability of 1, all else 0, the entropy of the system is 0 because there's no really uncertainty in the system. It's deterministic, right? So that's how we calculate for each token the uncertainty of the distribution. And the last chunk is where we really tie the two perspectives together. If you look into the mean attention, so for each token, we'll multiply their attention or significance by their entropy, right, which is the uncertainty, and also by a real word binary indicator to indicate like whether this word is a real word or not, and not just a filler word, right? We don't really care about like words such as and stuff like that. And once we calculate this value, if it exceeds a user-defined hallucination threshold, we'll count this token as a hallucination, right? So as a user, you pretty much just need to define what the threshold is, and you can do some testing that way. But this is how the model decides when a retriever is needed, right? Otherwise, it will just say stuff out of its own built-in knowledge. And the second point the model decides is what to retrieve. And the idea is pretty similar, right? Basically, it utilizes the attention matrix again, right? So every time it encounters an uncertain yet significant token, it will just look into the past context and select the most significant tokens and then pass them on to the retriever. And the third piece is what to generate. So the way Dragon works is that it will generate the output sentence by sentence, right? So, and the sentence is either free of hallucination, meaning it doesn't have any, none of the tokens exceed the hallucination threshold, or the sentence is supplied by a context, or like the retriever is activated. So in order to make this example more concrete, we passed the same query into the Dragon pipeline as well. And so you can see here, the same question is passed in. And if you just follow the printout, so the model generates 2 sentences first, right? This is all done on its own knowledge. This is no retriever is activated, right? But the problem is we run into in the second sentence, which starts by Dragon, which stands for dense retrieval. So right there, we know that's a hallucination, right? The model is making up a name for the paper dragon because it's probably past its knowledge cutoff date, right? So again, the model automatically detects the hallucination is in the second sentence, which is marked in red. The model automatically does that by doing the hallucination threshold, right? So, and after that, we look at the tokens that are significant to the word. Probably in this case, that triggered the retriever module is dense retrieval. So we look at the tokens that are significant to those 2 words, and then we send them to the retriever. So if you follow the printout, question to retriever, those are the tokens that are actually sent to the retriever. And again, the model automatically determines that. And so those words are sent to the model, and then I kind of redacted the context because you already saw what the context is, and I kind of wanted to save space for for this example. So what happens is that the model generates the new green text at the bottom on the left-hand side, which is replacing the original hallucinated text, which is the second sentence, right? So you have these two new sentences for this query, and both are supposedly free of hallucinations based on your hallucination threshold. So from there, we actually take those two sentences and pass them into the model again, and just have the model generate the answer all on its own. And unfortunately, the model, there's a new hallucination detected in the third sentence the model generates, right? And the same process is repeated, right? So you just determine like which are the tokens that are significant to the model, to the uncertain yet significant token, and just they're sent to the retriever, and then a new sentence, which is shown in the green, is attached at the bottom. So this is an example. This is a knowledge-intensive example, but you can easily imagine an example where some sort of reasoning by the LLM is required based on the retrieved information, right? So when the model doesn't need like outside information, and it only just needs to do the reasoning, we just leave it be and not supply any additional knowledge. But since this case is, this is a two-part problem, that's why the retriever module is activated twice, which is how it's supposed to work. Again, but this model is not for production ready at all. So we're just trying to really push the boundaries of what's possible of unfreezing all the components of a RAG system. And again, we're open for collaboration with anyone who's interested in this type of work. And with that, I just want to thank you so much for your time. And yeah, and like I promised, the citations at the end here, and these are the five papers that we thought were very influential to our research and go into production as well. So I think I'm done. Thank you so much for your time. Have a good rest of your day.